Chris Packer for the view of the metabolism of triglyceride and atherosclerosis of triglyceride and remnant, another topic, very complex.
I'll put up my first slide here. Okay. Back to triglycerides, folks, and what I would like to do is present to you some concepts that we're developing, and the we will become clearer as we go through, with regard to the metabolic aspects of TRL and their atherogenicity, particularly with regard to where remnants might come into the picture. Oh, okay. There's the disclosures. Right, there's a small delay here. The personal research that I'm going to quote today is a team effort with Professor Taskinen, who's in the audience, Professor Boren, and postdocs L.S. Bjornsson and Martin Adils in Gothenburg. And Professor Taskinen, can we go back? Professor Taskinen and I will give complimentary talks, but it's for you to judge whether I'm the warm-up act for Professor Taskinen's tour de force tomorrow. So I'll let you judge on that one. But please come back and hear that for sure. So I'd like to talk a little bit about the pathophysiology of triglyceride-rich lipoproteins and develop some concepts with regard to what is regulating what we have seen in the circulation. And particularly talk about the heterogeneity of TRL, because that must be at the bottom of the explanation as to why we seem to be confused about the outcome of clinical trials, and I'll develop that concept. Talk a little bit about type 2 diabetes and what goes wrong in type 2 diabetes, and Marsu will elaborate on that tomorrow. And then how you might regulate triglyceride lipoproteins, rich lipoproteins, using agents, and look at metabolic studies and some genetic studies that give us some clues here. In order to understand pathology, you have to first understand physiology. And our triglyceride transport system was developed to transport lipids from fast food. And the fast food that we're having in our ancestry is that kind of thing. We had to work hard to get our animal fat. So when we absorb the fat, about 95% is absorbed in the form of chylomicrons. It's extremely precious material because it's hard work to get hold of it. That chylomicron is released and degraded rapidly, and the lipid is stored under those molecular switches, the ANGPTL3s, 8s, and 4s, in adipose tissue. The remnants that are formed about 30 minutes later are cleared, scavenged by the liver by receptor processes that are very rapid. So there's a very efficient way of delivering what you've just captured into your adipose tissue. Of course, you want to capture your next meal as well. So when you do that, you need energy for skeletal muscle. The switches change. The liver generates large VLDL particles that are triglyceride rich, the liver's chylomicron. If you're a rodent, you actually make that with B48, not B100, but we make it with B100. It's converted to a remnant, and by and large, those remnants are cleared rapidly from the bloodstream. In the good old days when we injected radio-labeled lipoproteins, if you injected 100 to 400, SF100 to 400 VLDL, less than 10% of it went down the delipidation route. Most of it was cleared by the receptors in the liver. So that is completely analogous to what happens with triglyceride transport from the intestine. You need triglyceride when you're making babies, and therefore placental lipase is elaborated, and estrogen turns on VLDL1 production particularly. So what about, where's VLDL2, where's small VLDL, where's IDL, where's LDL? Well, the idea here is that small VLDL, IDL, LDL are released from the liver to transport mainly a small amount of cholesterol and some majorly important minor lipids that you need for brain development and brain maintenance. And indeed, these two systems of VLDL1 transport and VLDL2 transport at optimal levels are quite disconnected. Lipase is an extremely high capacity system. The receptors are an extremely high capacity system. So in order to prevent, say, VLDL2 being released into the space of dis and just cleared in a futile cycle back by LDL receptors, you need a counter-regulatory agent, and possibly PCSK9 acts as that counter-regulatory agent. When you're delivering triglyceride to tissues, you might not want all of your VLDL triglyceride to go into your right leg, so your left leg doesn't work because it's got no lipid. And you need a counter-regulatory action there, and possibly ApoC3, as you'll hear, is a major regulator of lipolysis in a systemic fashion. It allows you to take small packets of triglyceride, not the whole thing at once. So that's what physiology might look like if you have optimal triglyceride. Of course, what happens is, I tried pressing that, we actually have a minority of individuals in the population who've got optimal triglyceride. The majority have an overburden of plasma triglyceride levels, borderline, moderate, severe, or extreme hypertriglyceridemia. Overproducing VLDL in particular, as this slide shows, is what happens, but that tops out at about 1,200 milligrams of ApoB100 a day. To get real high levels of triglyceride, you must actually inhibit lipolysis, primarily with ApoC3. So that's why chylomicrons and VLDL accumulate as triglycerides get above about 5 millimoles per litre, but it's mainly VLDL that accumulates through a mixture of overproduction and under lipolysis at lower levels above 1.2. Let's look again at this spectrum of particles. If you're not optimal, then VLDL1 gives rise to VLDL2, IDL, LDL, and so it goes on. And you develop those ApoB100 containing lipoproteins. Chylomicrons appear in the chylomicron range, the least dense, D less than 1.06, and also in the VLDL range. We know from metabolic studies that when you have a fatty liver, when you have liver fat, either physiologically or pathologically, you overproduce VLDL1. So hypertriglyceridemia is an overproduction of the large triglyceride-rich VLDL. But now we begin to understand from recent studies what happens when you deliver fat to the intestine. Basically, you're producing triglyceride-rich VLDL containing B48, probably all the time. And then when fat ingestion takes place, a wave of chylomicrons and VLDL appear in the bloodstream, lasting about 6 to 8 hours, and then they are largely cleared, and you have almost none of that left at the end, except for that basal production. So that's what normally happens. And we now understand that VLDL is a mixture of the intestinal VLDL and the VLDL from the liver. In metabolic studies where we gave a fat load test on top of steady state evaluation of VLDL metabolism, these are the kind of pictures of metabolic rates that we came up with. And these are the rates of ApoB production in nanomoles per day, because of course B48 is half the molecular weight of B100. So the liver tops out at about 1,800 nanomoles of B100 per day. It develops VLDL1, or releases VLDL1, which has a residence time of about 4 hours. When you come to... Oh, that's gone on 2 clicks at once, but never mind. When you come on to look at a standard amount of fat that goes in, about 92 nanomoles of VLDL is released from the intestine on an ongoing basis. And then when you give a fat meal, another 380 or 200, about 500 nanomoles per litre of B48 are released in the form of chylomicrons, or VLDL1 particularly. If you look at the total amount of B100 released from the intestine, it's a significant proportion of the total amount of B48 released from the intestine is a significant proportion of the total amount of B100 released from the liver. So these are two organs that are generating ApoB-containing lipoproteins in substantial quantities. I gave you the picture of a normal triglyceridemic, less than 1.2 optimal triglyceride, and you can see there was no B48 left in chylomicrons at the baseline, and at small amounts. But if you're a hypertriglyceridemic, you have no chylomicrons left, but you've got large amounts of B48 in VLDL1 and VLDL2, and that's because they're not cleared sufficiently well from the bloodstream, and they live a long time. We figured about 5.6 hours on average. So that B48 pool of VLDL accounts for about 25 to 30% of all the particles that are in the VLDL range. So it's a complex, heterogeneous mixture that you see there. Can we go back? I did click it once, please. Yes, thank you. We know from metabolic studies that Masu and ourselves did a long time ago that VLDL1 production by the liver is under a fine control by insulin. If you take normal individuals and give them an infusion of insulin and measure the instantaneous production of VLDL1 from the liver, it shuts down about 50%, 60%. If you're insulin resistant, it doesn't shut down at all, so that overproduction continues. It seems also that insulin is an important regulator of B48 production from the intestine, because there's the relationship between insulin levels and the amount of B48 production. If you're insulin resistant, you overproduce B48. Typically, in some of our metabolic studies, if you give a standard amount of fat, you'll produce 200 milligrams a day of B48 if you're insulin sensitive, but if you're insulin resistant, type 2 diabetic, you'll produce twice that amount. Now, given that you eat the same amount of fat, then the triglyceride per particle, per B48, is less for the diabetic, smaller particles are produced, than the non-diabetic. So again, a heterogeneity is being introduced there. I'll just show this slide because ApoC3 in our hands appears to be the major regulator of both chylomicron lipolysis, B48 clearance, and VLDL lipolysis. And these two particles compete for the same lipolysis sites, and you can actually see that competition when you add chylomicrons into the mix with VLDL lipolysis. It pauses. And C3 is a major regulator of both of those metabolic steps. So that's something to hold in your mind for a slide that will come up shortly. So what about remnants? If you've got optimal plasma triglyceride levels, you produce a reasonable amount of VLDL, about 700 milligrams of ApoB100 per day. It transits rapidly through. Some of it is cleared from the bloodstream. Some of it makes normal-sized LDL. You have high lipase, low ApoC3. Your transient remnants are the bulk of what's going on, and your end product remnants, that is a remnant that sticks within the VLDL range and is not converted into LDL, there's a small amount of that. If, on the other hand, you overproduce VLDL, you have defective lipolysis due to C3 levels or lipase variants, then that transition is slowed. The ability to make end product remnants is increased, and you get more cholesterol ester being transferred in by CETP. And they have a prolonged residence time, as is shown you, maybe 6-8 hours instead of 2 hours in the case of a normal individual. And you can see this if you do metabolic studies. If you look at the top there, the low triglyceride group, give an injection of stable isotope labeled leucine, rapid clearance of the VLDL1, and a small amount of those end product remnants that are not converted, but hang around a long while in the VLDL1 range. But when you get to hypertriglyceridemics at the bottom, lipolysis is slowed, and the proportion that you find their way into those end product remnants is substantially higher, and you can see that in that red curve at the bottom. So metabolically, this makes sense. There are a mixture of particles present within the VLDL range particularly. So there's the pathophysiology, what normal looks like and what happens when you have abnormalities and increased remnant formation. So let's look at type 2 diabetes in particular, which was part of the feature of this conference. And this is all about overburdening the system. There you have a finely tuned system that is really there to make the most of the episodic, infrequent ability to get animal fat, or fat in particular, nutrients. And now we're eating several times a day, which we didn't do before, and we're not running it off to catch our next meal. The amount of VLDL1 ApoB that's produced is proportional to the amount of liver fat that you see in your liver from MRI studies. These are from old studies from Professor Taskin. And again, you can see there the HOMA index relationship to VLDL1. It's under insulin control as well. So you're overburdening the system and you're pumping out VLDL1 as much as you can because the liver doesn't want to retain that triglyceride. It wants it safely out into the bloodstream. Now, let's deal a little bit more with type 2 diabetes and what happens in the intestine, because this has been a picture that has been ignored for a long time, and we'll both touch on it today and tomorrow. As you can see, hypertriglyceridemia itself is not associated with overproduction of chylomicrons or B48 containing VLDL, but rather defective clearance, driven of course by the C3 that you just saw there. If you go to a diabetic, however, and this is our data and the data from Bruno Verge, you can see ApoB48 production goes up by 50% or even 100%. But it seems to be controlled not only by insulin, but by GLP-1 receptors. And agonists shut down that intestinal B48 production quite dramatically. See the effect there on chylomicron B48 production in the liraglutide study that we did. It was about halved. So there is a fine regulation of B48 release from the intestine that is being driven by factors beyond the factors that you see happening in the liver, because GLP-1 receptor agonists have no effect on liver metabolism. And again, you can see we didn't see a difference in chylomicron triglyceride clearance, but Bruno did. It went up about 50%. But the major effect of the GLP-1 receptor agonists was on B48 production. So this is a simulation that we did, Elias Bjornsson, taking the real life data and saying, okay, let's build 3 scenarios. Across the day, let's not just have one test meal, but let's have 3 meals and a snack. And what do the particles look like? Well, on the left-hand side, you can see if you have optimal triglyceride metabolism, you have a small amount of VLDL2 B100, a smaller amount of VLDL1 B100, and then if you give a fat meal at time 0, or not a fat meal, if you start at 8 o'clock in the morning and then have breakfast, lunch, dinner, you can see it builds up, and that's a bit like the Scottish hillside. Builds up over the day, but those clear pretty much by the end of the day. If, on the other hand, you've got fatty liver disease, obesity, which is accompanied by overproduction of C3 to inhibit lipolysis, VLDL overproduction, then the mountain levels climb up a bit, and you're looking at quite significant peaks of B48 containing lipoproteins and B100 containing lipoproteins. When you get to diabetics and overproduce those chylomicrons as well, you're looking at the Atlas Mountains here. There you can see across the day the large amounts of B48 containing lipoproteins and B100 containing lipoproteins. If we just rely on the snapshot triglyceride measurement at fasting, you miss all of that stuff. And that's why we need to pay much more attention to what happens across the day in the postprandial phenomena in terms of their atherogenetic potential. So to touch on something that we talked about this morning, what about TRL cholesterol as a marker of risk and as a marker of benefit? Well, here is the soup of particles that I've just described to you. Chylomicrons and their remnants in VLDL1 and VLDL2. Transient remnants, end product remnants throughout the ApoB100 delipidation range. All of that is TRL remnant cholesterol when you measure it. So it is associated with risk, and you can see that epidemiologically and genetically. But when you introduce a change, which particles are you altering? Are you altering them all beneficially? And is the change in the biomarker necessarily resulting in a change in risk? And in the prominent trial, that wasn't the case. So that's one question. The other question is statin therapy. If you give statins to somebody, they take out the remnants out of the system, particularly the end product remnants. I haven't had time to go into that. I'll touch on it later. But leave a lot of other particles in the circulation. And if you have removed all the remnants and then give something like a fibrate on top of that, what are you producing other than a biochemical change? Are you producing a change in the atherogenicity of that soup of particles? What we really need are better biomarkers of TRL-associated risk. There must be biomarkers of these particles and their constituent lipids and proteins that will give you a better index of risk and a better index of benefit. What we mustn't do is be too simple in our approach to TRL. Okay, in terms of intervening, what insights can we get from recent metabolic studies? And then I'll just touch on genetics at the end, because there's an issue that has been worrying us for a while, and there's some clarification appearing. Statins and PCSK9 inhibitors, are they the same? Well, metabolically, I'm afraid they're not, when you look at triglyceride-rich lipoproteins. Some old studies that we did on statins showed an increase in the clearance rate of large VLDL, small VLDL, IDL, and indeed LDL, and they were all cleared in hypertriglyceridemics by about the same rate, about a twofold increase of all of those particles in terms of their catabolism per day. But if you give a PCSK9 inhibitor, the recent article that we generated, VLDL2, small VLDL was cleared rapidly, IDL was cleared rapidly, but large VLDL was not altered in its metabolism at all. Jerry Watts did some turnover studies with chylomicrons, looking at postprandial lipemia in normal subjects here. There you can see the effects of statins that are well known. It increases the clearance rate of chylomicrons and their remnants. Look at evolocumab, absolutely no effect at all. So like VLDL1, no effect on chylomicrons in terms of PCSK9. And PCSK9 inhibitors are a poorer triglyceride-lowering agent than statins in hypertriglyceridemics. What might be happening? Well, the clue probably lies in which receptors are being turned on. And the only way of explaining this, I think, is to say that the clearance of VLDL1 is being accelerated on a statin, but not on a PCSK9 inhibitor. The clearance of VLDL2 is being accelerated by both, as is IDL and LDL. And the clearance rate of chylomicrons and their remnants accelerated by statins, but not by PCSK9 inhibitors. So the suggestion being that a different receptor is clearing the remnants of VLDL1 and chylomicrons from those clearing the VLDL2, IDL, and LDL. PCSK9 inhibitors turn on those receptors, the LDL receptor, but not the receptors responsible for remnant clearance as far as we can see. So that's a clue from metabolic studies. Something might happen here. Okay. So that's what's happening at the top end of the range with the largest triglyceride-rich lipoproteins. What ability do we have to control what happens further down the delipidation scheme when we're looking at those remnant formation and the ability to clear remnants by the liver or the ability to convert them into LDL? Here the agencies of lipoprotein lipase, endothelial lipase, and hepatic lipase play important roles, but also in determining what goes on here, ApoE, LDL receptors, PCSK9, C3 and ANGPTL3 seem to control this pathway, this branch point. Clearance by the liver of IDL, VLDL remnants versus conversion to LDL. And ApoC3 and ANGPTL3 to control the decay or the transfer down the delipidation chain in terms of lipoprotein lipase and endothelial lipase. I'm not going to go into these in great detail, but inhibitors of C3 have shown some interesting effects on triglyceride levels, VLDL cholesterol levels as a marker of remnant. No change in LDL, or a small increase in LDL cholesterol there. And both ourselves and Gisette Reyes-Sofer in Henry Ginsberg's lab have looked at C3 loss of function mutants and shown that there is a very rapid transit down this pathway if you lack C3 or are heterozygous for C3, just shows how powerful an agent it is, but no change in the production or clearance of LDL. So if you have a beneficial effect here, it's to do with remnant removal and transit, both of the transient remnants and the end product remnants. And we were able to show that the remnants themselves are controlled by C3 as well as the transit down the pathway. Another promising agent, of course, is ANGPTL3, and there have been a number of studies, but as yet no kinetic studies of ANGPTL3 deficiency that show that triglyceride can be reduced, VLDL cholesterol can be reduced, but also LDL cholesterol to a varying extent, and we don't understand why it varies so much. 7 to 10% in individuals with raised plasma triglyceride, but 30 to 40% in individuals with homozygous FH, and then there's the latest study down here. So these are agents that will allow us to control this part of the pathway, targeting ANGPTL3, stroke 4, stroke 8, and C3, and we're yet to discover the true potential in terms of risk prevention. A couple of remarks on the genetic studies, because from some of the genetic studies, it's come out that all ApoB containing lipoproteins have the same atherogenicity, be it a large VLDL, a small VLDL, IDL or LDL. And intuitively, that's a difficult thing to take on board. Part of it was the fact that in Mendelian randomization models, triglyceride became non-significant if you added ApoB in the model. But recent studies have shown actually that triglyceride is still significant on a per standard deviation model, standard deviation change in terms of risk prediction. What the authors haven't done in previous studies is looked at the change that they're looking at here in terms of particle number. If you change ApoB by 1 standard deviation, you change it by 24 milligrams per deciliter. But if you say, I'll compare that to the change of 1 standard deviation in triglyceride, you're only looking at about 4 to 6 milligrams of TRL ApoB. You're not comparing apples and apples, you're comparing apples and oranges. So we have to compare things on a per ApoB basis. There's been one study recently that has intrigued us, which shows the following. This is from the Helga Icelandic study. And again, they used a cluster analysis, not single gene analysis, a cluster analysis of ApoB variants and a cluster of variants that affect non-HDL cholesterol. And the answer that they came up with was adding non-HDL to a model that includes ApoB improved risk prediction, like adding triglyceride here. But adding ApoB to a model that included non-HDL did not. And the variants that got added to improve risk prediction were those associated with remnant levels. So there's an emerging evidence here that not all ApoB containing lipoproteins are equally atherogenic. And I think that's an important thing to build on. So I'm going to finish with this slide and then some conclusions. There's LDL. Oh. There's LDL. Can we go back a bit, please? Go back one. There's LDL. It contains about 2,500 moles of cholesterol per particle. It's a very simple looking particle. And that is delivered to the artery wall and causes cholesterol deposition and all the things that we understand. But if you look at a remnant particle or a triglyceride-rich lipoprotein, it has a very heterogeneous collection of substances on its surface. ApoB does bind it to the proteoglycans, and it can transmit that lipid load into macrophages. But what you have is altered fluidity on the surface of the particle that you see in type 3 hyperlipidemia, B48, an altered conformation of B100, the accumulation of 2 to 3 times more cholesterol per particle, partial lipolysis products in terms of mono and diglycerides, and altered apoprotein contents. I just don't see intuitively how that particle can be equally atherogenic with that particle, and some of the new genetic data is suggesting that is not the case. This is more atherogenic. By how much, we're yet to find out, but that means that altering the levels of these in the way that I've described might be particularly beneficial. So let's finish with some thought experiments. Does it matter how you lower plasma triglyceride levels? I did click here. Let's look at the various mechanisms. The first thing you can do is control VLDL1 production. Limiptide, mipamersin, that's the best way. Stop the stuff getting into the circulation in the first place, reduce the number of ApoB-containing particles. And the studies this morning on PCSK7 were very triggered in my mind that this would be a great way of actually reducing B100 synthesis from the liver in terms of large VLDL particles and their remnants and contributing to atherosclerosis. We can control the release of chylomicron B48 and the number of chylomicrons on the remnants that appear in the circulation without altering the efficiency of fat absorption. So that's an attractive mechanism with GLP-1 receptor agonists and others like it. Increasing lipolysis was top of the list at one point, but we've yet to see the benefits of blocking C3, blocking ANGPTL3 in terms of risk reduction. If you're just moving particles into remnants and the remnants are sitting there, possibly that's not as effective as blocking the synthesis of these things. Fish oils block synthesis, reduce it. Fibrates increase lipolysis, prominent. You can see where I'm getting to with that particular argument. Obviously, statins are great. They increase the clearance of all kinds of particles from the bloodstream, and you must remember that part of the benefit of statin therapy is to remove remnants as well as LDL from the bloodstream, and blocking the formation of cholesterol-rich remnants. Why didn't CETP inhibitors work better than they did? That's a big question, and maybe obicetrapib will help us out there. So, thank you for your attention. The conclusions are that TRL and remnants do contribute to residual risk, which is the feature of our conference. But the spectrum of those remnants is highly heterogeneous, and a change in TRLC may mean that the intervention is not as beneficial as we thought it was on the basis of its biomarker of risk. Have we got too simple a view of triglyceride-rich lipoproteins? We can only simplify it when we understand what's going on particularly, and that's what happened with LDL. We need to do the same with TRL. We need to investigate further the benefits of controlling the conversion of IDL and remnants into LDL as a potential therapeutic focus, and we surely do need better markers of remnant pathophysiology and the relationship of remnants and TRL to risk. Thank you.